That was a good break. That was a good break. You guys missed out. Lots of fun with liquid nitrogen. We ate frozen Rice Krispies, frozen M&Ms, and frozen Takis. I think it would go, personally for me, it was Krispies, Takis, M&Ms.
Yeah.
M&Ms didn't really change much.
It just burned your tongue.
Yeah, it burned you. So, we're actually going to do a quick lab. It'll be quick. On 31 this week to explain torque. So torque is the force that makes things rotate. So in question, we're on 31. So torque, do you remember what torque was? Because you're my first period person right now.
Yes.
What was it?
With
Oh no. What was the equation for torque?
torque equals I.
No.
No.
Force times R. Where R is the how far you are from the axis of rotation, and F is the force that you're applying. So torque is the thing that makes things rotate. So the acceleration, this rotation acceleration is net torque over, not M, but what do we use now? I. Net torque over I. So when the torque are balanced, what can you tell me about the rotational velocity?
It's either constant or
Yeah, so the velocity is going to be constant, either moving or not moving. Just like when the net force was balanced. So when the torques are balanced, the object's not moving. So we at 31, the figure above shows a uniform meter stick that is set on a fulcrum at its center. A force of magnitude F towards the bottom of the page is exerted on the meter stick at the position shown. At which of the following positions must an upward force of magnitude 2F be exerted on the meter stick to keep the meter stick in equilibrium? So what do you guys think right here? The net torque needs to be, we want the net torque to be balanced. So the torque needs to be equal to each other. So we have, what kind of force do we have this way?
mg.
Well, before it was F and the distance was, let's say R, and now it's 2F. So what do we know about R?
R has to be bigger.
This R needs to be bigger than this one?
I think smaller.
It's, regroup our thoughts because we're all very excited. So here we have 2F. So here we have F times R equals T. So 2F times something has to equal T also. So it's going to be half R right there. So the answer is going to be B. Let's picture Y though. Because you said maybe C, right? So we have this thing like this. This force is pulling down, right? And what do I know about my 2F force? Pulling up. So what would happen if I put an up force right here?
It'll go down on the other side.
You're calling, so right now, this thing is rotating this way. Like, can you picture this thing like a seesaw moving this way? What if I just have a force right here going up? Which way is it rotating now? The same way? Yeah, it's still going to go this way. I don't want it to rotate. So now, Do you see now why if I have them like this, it's gonna spin even more?
Okay, yeah.
So that's why we put it right there
Oh, okay.
and closer to counteract that. So that's why the answer right there is B of 31. And again, this will go over and we'll have a lab on this week when we do the dynamics of forces. 32. Go ahead and do 32 for me.
Hello.
So I feel like this one you should be able to knock out some immediately. That's right. Good job. You knock out those. So, in a classroom at time t0, a sphere is thrown upward at an angle of 45 degrees to the horizontal. At time t1, while the sphere is still rising, it bounces off the ceiling elastically and with no friction. Which of the following pairs of graph could represent the sphere's horizontal velocity and vertical velocity? So, let's talk about what's going on. You have two velocities, right? What can you tell me about the horizontal velocity?
It's gonna stay constant.
It's going to stay constant. So you should have knocked out C and D. The horizontal velocity doesn't change. So now let's talk about, usually, what happens to the vertical velocity? The vertical velocity gets smaller or bigger as it goes up?
It's small.
Until it gets to the top, and then once it gets to the top, what happens?
It becomes.
It comes in the opposite direction and starts speeding up or slowing down. So, this was the vertical, right? The Vy. It starts, has a velocity, and then gets this way. And then, what happens to the velocity after? So now it's decreasing velocity, it hits zero velocity, and then it gets bigger, right?
Yeah.
So should it go like this, or should it go like that?
Yeah. Downward.
Why not this way?
Because you're speeding up to the positive here.
So if I do this, what didn't happen?
You didn't change direction.
You didn't change direction because the sign didn't change.
momentum into it, it would keep bounces on.
It would be like if it went like this, stopped, and then kept going like midair. That would be weird, right? Imagine I throw something, stops in midair, and then keeps going the same
I
direction.
mean, it's possible with the tennis.
But when it goes, and then it goes like that. So it should have been,
That's breaking reality.
it should have been like this, which is what A looks like. But that's not what happened in this. That's usually what happens. But this one, what happened was, Y was still rising. So it hadn't reached the top yet, right? It hits the ceiling. So when it hit the ceiling, it was like somewhere right here. That's when it came to an immediate stop. It hadn't reached by itself, it hadn't slowed down, and that's. And then it went this way. So do we see why it's B and not A? It's that while it was still rising. If they were to tell you it goes up and then comes down like nothing would have interrupted, then it would have been A.
Right, so it's B.
The answer is B. So, two satellites are in circular orbits around Earth. Satellite B has an orbital radius of 9 times the satellite A. What is the speed of B?
It's a whole radius.
So, the answer in this one is B, but we haven't learned this stuff yet. We're going to learn conservation of angular momentum. So angular momentum is, we said it was L is the symbol for momentum when it's in a circle, when you're rotating. And now it's what times what?
Radius
I times W.
I times W. And I changes with the R, right? So as I gets bigger, the velocity gets
small.
smaller. And we'll look at conservation of angular momentum right now, but this was a problem of conservation of angular momentum. 34. Remember when I told you I didn't teach you about center of mass? And I'm going to do like one day where I'm just going to tell you the quick rules. I'm just going to tell you one of the quick rules right now. One of the quick rules. How does the speed of the two-car system's center of mass change? Anytime you get a problem that is center of mass speed, the speed of the center of the mass, the speed of the center of mass never changes. The answer is A. So, and I'll show you lots of problems if you want where they ask you the speed of the center of the mass, that never changes. When you guys get a problem like this, it's always going to be not changes or 0. Not changes, it's 0. The speed of the center of the mass. And I'll tell you guys why. I'll show you some videos why. But on the test, I've only seen it pop up like this. So if you guys see something of speed, center of the mass, does not change.
So
35. Two astronauts are connected by a taut cable and are initially at rest with respect to a nearby space station. So astronaut X throws a large container to astronaut Y. Okay. Figure 1 shows the astronauts immediately after the container was thrown by astronaut X, and figure both shows the figure 2 shows the astronauts immediately after the container is caught by astronaut Y. Which of the following describes the motion of astronaut Y in figures 1 and 2? So they're tossing it back and forth?
Mm-hmm.
Is it B?
Astronaut X throws a large container to astronaut Y. Figure 1 shows the astronauts immediately after the container is thrown by X. And figure 2 shows the astronauts immediately after the container is caught by Y. Which of the following? So are they I don't understand if they're tossing it back and forth.
Yeah, they're tossing it back and forth. Wouldn't it be B? Yeah,
Yeah, because
it's B because they're not showing when they catch it yet. It's just when it's thrown and what happens to Y.
Figure 1 shows the astronauts immediately after the container is thrown by X. That's what I don't get.
So it doesn't show when Y catches it yet, just when it's
says-
already thrown.
But figure
But-
1 shows. Wait, guys, wait. Let me speak to this part. Figure 1 shows the astronauts immediately after the container is thrown by X. So if he just threw it, he shouldn't have it in his hands, right?
Yeah.
Immediately. So why does he have it in figure?
Maybe like
One.
they messed up, maybe like a typo? It's not in this, he's not, like,
You see my problem now?
yeah, I get what you mean. But he's not holding it, it's just like in the area of his hands. No, he's holding, oh yeah, you see, he's not like it's like
grabbing
this is where it is, and it's already being thrown like that.
Yeah, you see how there's like a tiny little space.
Like there's
You're
this
saying like
space-
right immediately, like
That's what,
like
yeah,
the
I see the
instant
little
right
space.
after.
Like there's a tiny little square right there.
Yeah, there's
a
like
little
a
white
tiny
spot.
space.
I never thought
Do you
people
see
were gonna do that.
So think of it like this, it's like the little tiny millisecond of it leaving.
Okay.
It's like
So-
the thing where you said about the pencils. So they'd move to the left and then they'd move to the right.
Anyway, the answer is D. And
Thank you,
let's
bro.
think about. Well, let's think about what happens to each one.
Why does it not move?
I get why it would move to the left, because when the guy throws the...
Yeah, when he throws it to
Yeah.
the right,
He goes to the left.
He goes to the
Oh,
left.
I see why it's not that.
Well, why wouldn't it move to the right when he catches it?
so what happens to the guy to the when that makes
Oh, when it's caught? What?
Because when he gets it, he should like have that like little instant like,
No, it
But they're-
doesn't because
they're
it's
connected by the
already-
cable, right?
Yeah.
So what is Y doing?
It's
The moment, so when I throw it that way, right?
Yeah.
I start moving this way, right? Cool. So if you're connected to me and I move this way,
I'm gonna do that.
you're gonna move this way, right? And then later,
when the
You're moving
spin
this way.
goes.
and then you catch something, so now you're back this way.
Oh,
What
I
do you
think
mean?
you
Like
balance
To the
it.
right?
The two forces,
Balance.
the pull that you just experienced
Cancels out with the
cancels out with the
Apply.
push that you're getting by the
Alright.
can.
Oh.
Dang it, I got them wrong.
I took
Ah.
yeah, because
36. But that picture still makes no sense to me.
It should give a better picture.
The graph above shows the force exerted by a spring as a function of the length of the spring. A block on a frictionless table is pushed against the spring that is fastened to a wall. The spring is compressed until its length is 20 centimeters. The block then released. Which of the following is the closest to kinetic energy where the block leaves the spring? Okay. So if I want to know the kinetic energy it leaves the spring, what do I know that it is equal to?
the potential spring energy.
The potential spring energy that it has. So I have to find the, does that make sense what Hector just said? The kinetic energy of when it leaves the spring is going to equal to the potential energy when the spring is compressed. So ultimately we're looking for 1/2 kx squared cool. So we know that the spring is compressed how much? 0.2 centimeters, 1/2. So how can we find the K?
We use Hooke's law. Or no?
We can find the slope of that graph.
That's the key right there. And this is one of the things that it's testing, this problem's testing a small detail right here. That's why only less than 1/4 of kids got it right. It's testing a small detail. What kind of graph do I have right here?
What's over the or
Force
displacement?
and displacement.
So it's force, and then the displacement of the spring, right? So when I find the slope, what am I dividing? I'm basically dividing this by this, right? So velocity times time. If I find the slope, it's like dividing v divided by t gives me acceleration, which is my slope. So what is f divided by change of x? It's Hooke's law right here. The spring constant. So F equals change of x times k. That's Hooke's law right there. So the slope right here is the spring constant. And that was mentioned, did you remember that because of the video that you just watched? Yeah. I'm not sure if you watched it. I need to grade those this weekend. So when you guys watch the work energy videos from Flipping Physics, this is one of the things he mentioned. And then I also mentioned it in class when we were doing Hooke's law. Where if you have a spring, the force on the spring, the displacement kind of graph, the slope will give you the spring constant. The change in energy will be given by the area under the curve also. So once you find K, you can find it because you're going from 60 to 0. So 60 divided by 0.1, rise over run, and you will get the answer to be A.
A?
Yeah. Go ahead and try 131. answers. Interesting. Okay. Let's look at this one together. Toughie right here. So this is what I am doing for right here. I1. When they ask you for the potential difference, what are they asking you to find?
Voltage.
The voltage, yeah. So they're asking me, how can we find the total voltage? And in series, every time there's a voltage drop, right? You start with the voltage of the battery, and with each resistor there's a voltage drop. So the voltage drop should equal to 0 at the end. That's why they all equal 0. So these two are what to each other? These two voltages are equal to each other if it goes this way. The voltage drop should be equal to each other. So I can rewrite this as it's way too ugly even by my standards. I can rewrite it like that, right? Yeah. So if I want, so it's going to be V minus this one and that one, right? So I'm going to have V minus because I'm trying to like, there's a lot of math here. These two voltages, I'll just do it like this. I3 R4 minus I3 R3. You see how you guys see why I put V equals I for each one of these? Is that verb right there? The current times the resistance give me the voltage drop right there. So if I have this right here, what do you guys see I can do right there? Well, I can pull out the I. So that gives me I over R4 minus R3. So that's where a lot of these are coming from. So these are in series, right? So what do I do with those then? I add them. So the voltage drop here plus the voltage drop there, that's what I'm going to subtract from this voltage. Does that make sense?
Not that much.
Okay, I see your face.
Yeah.
So let's do a vert table for these right here. One, two, three. 1, 2, 3 total. And I know the total voltage drop, right? Is V. So what happens if I subtract the voltage drop from here minus this one, minus that one, minus that one? What number am I going to get?
0.
0, yeah, because all these three add up to this one. So if I subtract, so do you see like where that comes from? Okay. So now, let's say that this was 6 and 7 and 8, right? So I know that minus 8 minus 7 minus 6 gives me 0, right? So can't I say that V minus 8 minus 13 gives me 0? So that's the same thing I'm doing over here.
Oh.
These two are that's what goes right there. So that's what they're doing on number 1. On letter A.
Yeah.
Those two right there are that current right there. So these are in series, so that's why they're subtracting them like that. So V minus, then I3, because I factored out that thing, R3 plus R4. And then I have to worry about these two over here. And what do I know about these two voltages? They're the same, right? So does it matter if these two numbers are equal to each other? Does it matter which ones I use? So that means right here I can put in I1 or R1. Does that make sense to you? Why I can put this one or that one right there?
Because of the same.
Yeah, they both equal the same thing. Yeah? Okay. So that's why A is one of the answers right there. The other answer is since these two are equal in voltage to each other, right? I could have put I2 over R2, right? That also could have been right. Look at the C. That's what they did right there. They flipped these two to give you this right here. So the answer is A and C in that one. Do we get why? It was a long one to explain. Hopefully not a completely long one to do. But it was long to explain because of why they factored out stuff and why we could have used whichever one, right there. 132. Two lap carts have the same mass and are free to move on a horizontal track. The cart's wheels have negligible mass. Travel one at 1 meter per second to the right and collides with the two, which initially at rest is shown above. Cart 2 has a compressed spring-loaded plunger with a non-negligible amount of stored energy. That means we can ignore the energy in it. During the collision, the spring-loaded plunger pops out, staying in contact in cart 1 for 0.1 seconds as the spring decompresses. Negligible mechanical energy dissipates during the collision. Taking a word positive, the cart's velocities after the collision should be which of the following two answers? Such a long problem. Let's skip to 133. I'm coming back to it. Maybe. I'll tell you guys why. A block of mass M is at rest on a rough incline. That means there's friction. Which of the following forces must have a magnitude equal to mg? So go ahead and try that one, please. One of the answers should be fairly obvious. I like this problem because it's an example of why not and why yes. What do you guys get?
D.
D and did everyone get D at least? So D is 1. mg is equal to the gravitational force. Now let's look at the why nots. What's wrong with C? What is the force of friction equal to?
The
Sorry, G.
Yeah. Since it's on a mg sine of the angle, and the force of friction would be mg sine of the angle, because they're balanced. So that's equal to each other. The normal force exerted on the block by the incline,
No.
what's the normal force equal to?
Cosine of the angle.
Cosine of the angle, mg. So I know why I would choose D. I know why I wouldn't choose C. I know why I wouldn't choose B. It's the end of the test. I'm freaking out. I'm putting D and A. Or A, D, whatever. However you guys want to say. Those are the answers, A and D. Having a why not is very okay. So on 134, the tuning fork is held above the opening of a pipe that is partially submerged in water, shown above. The tuning fork is vibrating at a known frequency of F. Which of the following additional pieces of information by itself will allow for the speed of the air to be determined? Okay. So, what do we know in this problem? We know F. What are we trying to solve for?
The speed.
The speed. So what would we ideally like to know? Something to help us find the wavelength. We want something to help us find the wavelength. So if we want to find the wavelength, what is it that, one of the things that we would like to know? What kind of tube do we have right here? The wavelength is going to be equal to,
Okay.
Okay, close.
Well,
this is going to be an open closed tube. Because one side is closed by the water.
Is it
What?
4L over
4L over N. Do you see why it's a closed tube?
no. I don't see what you were looking at. So this one, isn't this one open?
Yeah.
Open?
Well, this side is open, right? This side is closed because the water's there.
So the waves don't go through the water?
No, not the airwaves.
Oh,
Like the water has its own waves, but we're talking about the air that we're going to hear. So the air that's vibrating, so when the tube is underwater, here's the water, and here's the top of the tube. The air particles are vibrating like that when it's the fundamental frequency. When it's the second one, it would be like that. So 4L. So if I wanted to know the wavelength, what information would I like to know? Trying to find the wavelength. So what do you want? What should I know? The L. I want to know what L is. What is the L at the first resonance? What is the shortest column that gives me a resonance? What is the smallest I can have LB that I still get a standing wave, a resonance? So that's why the answer is 1. The shortest air column that gives me a resonance. If I can have the smallest L, that will, do you get why it's A? So,
my shortest though? I want to be the longest.
because that's when it says the shortest column that gives a resonance. A resonance is a harmonic. So I want to know when it's the first harmonic, that's when L is going to be the smallest. So the more L I get, the bigger the wavelength. So like, what's the smallest I can have that I can still get a harmonic? So not all L's are going to give you a standing wave. just like not all frequencies are going to. So there's certain frequencies that give you a standing wave, right? So if certain frequencies give you a standing wave, not all wavelengths are going to give you a standing wave, right? So we need to find the shortest L that will give me a standing wave.
Oh, okay.
So the other answer is C, the difference between air column lengths that give two consecutive resonances. So if I know the wavelength for one and the wavelength for another one, I can find the difference to find the difference right there. Hi, sir. We're done. You came right in.
Okay.